will try and do is uh, first thing today will be just details about what we will discuss in the class. So first, let me go ahead and this is the outline of today's presentation. This is the first class, and most of you are not even aware of what manufacturing is, right? So how many people have some inkling? So either what you can do is either you can type in the chat box. We want to have some communication going here. So either you can type in the chat box, or what you could do is you could use unmute yourself and talk also. That's fine by me. It's a small class, not a very big class, so I think we should be able to handle that as well. And how many people have any semblance of what manufacturing is? Like what, in your opinion, what do you think manufacturing means? Any idea? Any of you?
Creating goods from raw materials.
Mm-hmm. So raw materials, and do what with the raw materials?
Process them, mold them, and like
Okay, sounds good.
transform them into raw materials for further processing or into finished goods.
Okay, so either you basically do some intermediate step or produce into finished goods. So that's one definition for manufacturing. So manufacturing, a unit manufacturing, what you said is right. You take some raw material or something, and then you change something there, either shape or a property. So you do something. Most likely what you do is you provide some form of energy, and then you change either the shape or the property of that thing, and that will be a unit manufacturing processes. But there is another definition of manufacturing, which is enterprise level manufacturing. So anything right from the concept to the recycling of the entire thing constitutes manufacturing. So I'll give you both the definitions of manufacturing, and so I think you have some semblance. So basically, I'll talk about contact details. My name is Ramesh Singh, and I'll be teaching you manufacturing processes one. My office is in Machine Tools Lab. Not that it is very helpful these days since you guys are online. So if you happen to return back, then we would do some of the projects here in the Machine Tools Lab. We'll still do the projects. We'll try to do some analysis, and if possible, somebody can help you make some small things. We will want to have a hands-on project as a part of this course. If you get back in time before the semester ends, we would have something in the Machine Tools Lab, which appears to be unlikely right now. But usually what we do, even till the last year when the semester was cut short, we had student projects in the manufacturing. I'll give you some of the topics of the projects. There will be a TA to help you. And then you do some projects which will have some credit associated with it. You can call me at 7507. You can email me. Whenever you need to talk to me, you can either have an appointment, or 4 to 5 Fridays I'll be available on some web platform. So you can have some discussions if you need to. And this is the class website. So class website is there. All the lecture notes will be uploaded. Of course, they will be there in the Teams files, and they will also be there in what do you call your website, your Teams course
Moodle.
files it will also be there. You have any questions? So basically, before we go into focus and objectives, I would show you a small video just to give you some semblance of what basically manufacturing does. This is a very old video, 1938. And what this does is this actually shows manufacturing of a locomotive. So let's see that video. It's a very interesting video. I will let me just start this video. We'll watch for a few minutes, and then I would want you to basically see what kind of processes go on in there. Is the video audible for you folks?
No, sir. No, sir. No, sir.
I don't know why the video is not audible. Let me do one thing. Let me just. I think it's probably because my. I'll change the.
Now
Is it
the
audible
frame
now?
is ready for assembly. Carefully,
Yes, sir.
Yes, sir.
alongside its twin, to which it will be
Is it
securely
audible?
fixed, ready
Yes,
to
sir.
receive
Yes, sir.
the cylinder.
Was it audible or no?
Yes, sir. Yes, sir.
Okay, good.
Yes, sir.
It was primarily because I had my Bluetooth on. So I'll start it again. Yeah.
The new engine makes its first appearance on paper. Over 370 drawings of the several parts have to be thought out and prepared, each one being passed by Mr. W.A. Stanier, the chief mechanical engineer. Plans approved, a specification is prepared. From this specification, orders are issued by the stores department. In due time, material starts arriving at the works. The main frames, which may be called the foundations of the engine, arrive in the form of flat steel plates, each 1 1/8 inches thick and weighing 3 tons. The first process is cutting them to the desired pattern. Oxy-coal gas cutters, working automatically, trace the pattern on the steel plate, guided by the template. Next, the slotting machine. This huge piece of mechanism, weighing 100 tons, eats through 10 plates at a time. Each tool is operated by a 20 horsepower motor. Drilling the plates to take the various rivets and bolts is done by a multi-boring machine, which drills any size of hole up to a diameter of 3 to 4 inches. Cutting, slotting, drilling, and the final trimming reduces the weight from 3 tons to 2 1/4. Now the frame is ready for assembly. Carefully, the plate is guided into position alongside its twin, in which it will be securely fixed, ready to receive the cylinder. Over 60 molds and cores are required to make a pair of inside cylinders for our engine. Skilled workmen fashion them in sand from patterns made of wood in a nearby shop. Casting time is an anxious time in the iron foundry. The cupola has to be tapped at precisely the right moment, and the 4 tons of white-hot seething metal taken to the site of the cast in the shortest possible space of time. The aperture into which the metal is poured goes by the name of the runner box. It acts as a sort of funnel. Metal may set too quickly near these plug holes, and these men, carrying out an operation called feeding, are preventing this from happening. 1 or 2 days to cool, and the mold is ready for breaking open. The crane, fixed to the actual cylinders, draws them away from the molding box. Men with crowbars break away the sand so carefully and skillfully fashioned by the molders. The final process is dressing and fettling. The cylinders, cleaned of all traces of sand, are given a rough trimming with the aid of pneumatic chisels. The first operation in machining the cylinder is milling the sides. Boring the cylinders is a tedious, though highly important job. The degree of accuracy demanded is of an exceptionally high order. Now for our first bit of real engine building, completed cylinders meet the completed main frame. Add the two outside cylinders, which have gone through exactly the same process as the inside cylinders, and the frames are ready to leave for the erecting shop. In the midst of modernity, the ancient craft of the smith still holds the place. Weight, of course, is useful in the smith, and we've no hesitation in affirming that the smith a mighty man is he. All manner of smaller parts are made in the smithy. Nuts and bolts in all sizes and varieties, rivets for the tens of thousands, washers, springs, and small forgings. They're all part of the grist that comes to the smithy mill. Batteries of machines, each designed to do a particular job, cut and drill the various parts of the boiler, searing through the tough steel as though it were cheese, until finally they are ready to be assembled. This gigantic machine applies little more than gentle pressure to force into shape the steel wrapper plate. First in the assembly of the boiler is the joining together of the three sections of the barrel. Here you see the various parts of the boiler laid out in line. Steel wrapper plate, foundation ring, top and bottom half throat plate, fire door plate, and the barrel. The throat plate is being attached to the barrel. Some 3,500 rivet holes have to be drilled. On this tower triple drill, the boiler can be rotated, moved backwards and forwards, and the drilling head moved upwards and down. The gigantic size of the boiler can be realized from this picture. Rivets, and more rivets, adding strength to strength. 250 pounds of pressure to the square inch needs a bit of holding, and hold it the boiler must. The inside copper firebox and the outer steel casing are securely held together by over 2,500 stays. The stays are screwed in and the heads riveted over. A modern engine, such as 6207, has a big appetite for steam. Hence her large grate area of 45 square feet and her high amount of tubing. First to go in is the main steam pipe, through the center of which will later go the rod connecting the regulator handle to the valve. Now the smoke tubes, of which there are 112, each 19 feet 6 inches long. The 32 superheater tubes are the same length. These are screwed to the firebox tube plate. Meanwhile, things have been happening at the other end of the boiler, and some familiar objects have been finding their way onto the fire door plate. Heat is precious, has to be conserved, and this is how it's done. Steel wrapper plate, foundation side cylinders, and the frames are ready to leave for the erecting shop. In the midst of modernity, the ancient craft of the smith still holds the place. Weight, of course, is useful in the smith, and we've no hesitation in affirming that the smith a mighty man is he. All manner of smaller parts are made in the smithy. Nuts and bolts in all sizes and varieties, rivets for the tens of thousands, washers, and hold it to...
So I'll stop it here now. Let me unshare the screen now. Okay, so I'll share the other screen where I can write. Okay. So let me ask you one thing. What are the processes which you saw here? Can somebody name the processes which they saw here? In this
Molding, welding, riveting,
one by one, one by one.
molding.
Molding. What do you mean by molding?
The where they poured the hot metal into that thing and then broke away the sand, the
Okay.
mold, sand mold.
It's called casting. Molding is a generic word, but molding typically is used for where you pressurize it. So it's probably for more for injection molding. But yeah, you're right that that's a mold. But the process is called primarily casting. At least in the metals, it is called casting. So you
Okay.
saw casting. What else did you see?
Riveting, when they were
Riveting.
fixing the two
Okay.
parts and they riveted it.
Mhm. So any particular reason why they were riveting? Is there another process which you can use in place of riveting? And do you see rivets, these many rivets anymore in general world now? To join plates, what is the process you use? You have done your first year workshop, right? What do you use for
Uh,
joining processes these days?
Welding.
Welding.
Welding, right? So why do we? So earlier welding processes were not there, right? So we had to use riveting, but now we have welding processes. So you don't need riveting that much. If you see the old bridges, you remember those old British era bridges, which the truss bridges, which you see of painted with red metal oxide. How many people have seen such old bridges with like red metal oxide paint, which is like total metallic bridges, old bridges, British era bridges?
Yes.
Have you seen that? Nobody has seen that, is it?
No, sir.
No, sir, we have been.
You have not seen the metallic old school metallic bridges. None. Railway bridges, have you seen those railway bridges made of metal?
Yes.
Yes, yes, sir.
Yeah.
How many people have been to Calcutta and seen the old Howrah Bridge? So if you have not been, the old bridges, right? These bridges are all riveted, primarily because we did not have a good joining technology. So now that we have good joining technology, we don't need to use those many rivets. So it's welding is the preferred process of joining. So today, if you want to have those boilers which you saw, which were made for this locomotive, unfortunately today we don't use steam boilers for at least not for locomotive purposes, but we use it for power plants. And almost everything is welded now. All the pressure vessels today are welded and not riveted because welding has evolved and welding is a better process as of now. So that's why people use welding more than riveting these days. But riveting is still used at one place, which is very common. Can anybody tell me where do you see rivets these days? Still reasonably common. And I'll give you a hint that this is actually a mode of transport.
Is it ships?
Ships little bit,
Aircraft.
but more common there. Aircrafts. If you have you looked at the aircraft wings, the entire wing is riveted. The fuselage is riveted. Fuselage is the central part where you sit, the cylindrical tubical tube part where you sit. Those are riveted primarily because they're made of aluminum and you need high strength and you don't want so welding aluminum is not easy. So most of the aircrafts are riveted, and riveting actually gives you long life. So riveting still is used. Of course, ships they use it, but aircraft still riveting is used quite extensively in aircraft in airplanes. So basically, what we will do in this course would be what one of your colleagues was suggesting: molding, which is casting, right? So we'll cover casting, we'll cover joining, not riveting primarily, but we'll talk more about joining processes as in welding. Deformation processes, which you see the guy was hammering the hot metal, right? That's one of the oldest processes which human beings discovered. All the swords, right? All the swords, everything was made by forging, because forging gives you high strength. Any ideas if I deform the material, right? Especially if I do cold deformation, not hot deformation, cold deformation. Although deforming cold material takes lot more energy than a hot material, because hot material is very soft, right? So if you heat the material, material becomes soft, and then you can deform it very easily. So that is one way to deform it. If I do cold deformation, then the material becomes very, very strong. Anybody knows why? If not, we'll discuss it when we go to deformation processes. And deformation processes, if you saw the video, there were two kinds of deformation processes. One was big chunk of metal was being deformed. And if you remember, there was one where you are making the boiler tubes. You are bending the sheets. So there is bulk deformation and sheet metal deformation. So you do two kinds of deformation processes. And then polymer processing, which is primarily molding. So can somebody tell me what is the defining connection between these, between casting, joining, and deformation processes and polymer processing? Is there a thread between all these? Why are you choosing these processes? And can somebody tell me what other processes is in that video you noticed?
Sir, one was drilling.
Drilling. I'll just write it down for the sake. Drilling. What else?
Sir, one was milling.
Milling. What else? Anybody? Drilling, milling.
The forging was also there.
Which was? What was
Forging,
that?
forging.
No, forging I've already used here. Deformation processes is forging actually. So I'll just use these processes. Let's say boring also. So I am not talking about these three processes. I'm not talking about these three processes. Why? I'm only talking about casting, joining, deformation process. And so I'm talking about casting, I'm talking about joining, deformation processes, and polymer processes. Polymer processing. Only these processes. Why?
So because probably they're used for manufacturing of components, and the later processes are used for further machining of the components.
Okay, so the reason is a bigger reason is because that's how your course is structured. In Manpro 1, we only cover mass conservation processes or mass addition processes. Machining is an independent course by itself, which you will do in 338. So basically, what we will doing would be subtractive processes we will not discuss here. So machining is drilling, milling, turning. All these processes will not be talking about here. We'll only be talking about mass conservation, where we conserve the mass or we add the mass. Right. So that's why these are the course, these are the processes you'll discuss in this course. And what we would do is we would develop first order mathematical description, because you're an engineer, right? So we need to understand. We are not technicians, right? We need to understand the process, how to make it better, what is required. If somebody, you are a practicing engineer, somebody tells you, I have this material and I have to make this shape. Can you recommend what size press I need? So you need to be able to have some sort of a tool with which you can analyze the process and predict what kind of forces will be required and the power to drive the hydraulics or the motor system would be required. Right. So these things you have to be able to know. So I'll basically say that the first order mathematical approximations of the processes you will do, and that you will do for temperature. Why is temperature important? Can somebody tell me why is temperature important in the first place? For which process temperature will be important? Can somebody tell me that? Now you know that we talk about casting, we talk about welding. Is temperature important in casting? Should I know the temperatures, how temperatures evolve while we do casting process? Will that be an important thing for us?
Yes, sir.
Yes, sir.
Why?
Because we
Why would
need to
temperature
decide
matter?
when to break the mold.
Pardon?
Because we need to decide when to break the mold.
Okay. So a lot of people agree the temperature is important. More than breaking the mold, that's one thing, because we need to know how it cools down, right? We need to know what is the
Yeah.
rate of cooling and how the temperature comes out when it is at room temperature. Agar bigger problem is while you are pouring it, you saw how big the casting was, right? That engine casting. Now the question is, what if the material freezes in between?
Yeah.
Right. So we need to understand what kind of superheat we have to give. What is the rate of cooling? It should not cool midway. Otherwise, what will happen is your entire casting will go to waste. So you need to understand what are the temperatures, what is the melting temperature, what kind of overheat what kind of uh, overheat we need to give to make sure that the temperature doesn't really go below the melting point while it is filling up. So all this analysis we should be able to do. Where will forces be important? Forces and power be important. I gave you some example, right? When I'm forging, right, I need to deform the material, right? When I deform the material, how do I estimate what kind of forces will be required? Any ideas? I understand that you haven't really thought about it, but imagine I have a simple, say, cuboid block, right? And I'm trying to press it to deform. Tell me some idea, how do I estimate forces? If I were to estimate forces, a very, very basic idea to estimate forces. I have a cuboid piece. I want to compress it, make it flatter.
Then it will depend upon its like Young's modulus and that thing.
Okay, so let me just bust your bubble here. Nothing will be Young's modulus driven here because you're way above elasticity.
Yes, yes.
Right? Because you're deforming it plastically. So you would need the plastic behavior of the material. That's very correct. You need some sort of a stress-strain relationship. Unfortunately, it will not be Young's modulus. It will be a non-linear behavior.
Yes,
So
yes.
we'll talk about it a little bit in the course. I understand that you haven't read that yet, but we'll develop all these correlations and we'll tell you what kind of strains would come. So if you know the stresses, if you know what kind of stresses would be required, I can basically do a stress times area and get a force estimate. I can get about the shape estimation. If I know the strain, what would be the final height post deformation? I can get final shape. I can also estimate in some cases what time would be required to do the process. So these are some of the things which we need when we analyze the process. And we also need to understand the capabilities and limitations of unit process. A unit process is defined by one process, right? If I have to make a train, I have to do a lot of these processes, right? I have to do casting, I'll have to do riveting, I'll have to do machining. All these individual processes are called unit process. So what we will be studying in this course will be unit process and understanding how a unit process works. What is its capability? How do we do first order mathematical approximation of the process? So we'll understand the process and we'll also understand the quality which it can give and productivity which it can give. Let me ask you a simple example, right? I have to make a say maybe for a lack of better word, I have to make a piston. Let me just say I have to make a piston. This shape of a piston, you know, a piston is like a cylinder. It's like a circular, say circular plate, right? With some sort of a connecting rod. Now, what kind of process I can use to make that? Can anybody tell me what kind of process you'll use to make a just as basically a circular, for the lack of better word, a circular plate? How do you make it? How can you make it? What are the processes you have with which you can make that? Any ideas?
So one thing that forging will be there.
Okay, so you can do forging. You can take a different piece and make it. Actually, casting is one process. Yes, you can do casting. You can do machining. You can do forging, right? Or let's say you can also do additive manufacturing. Nowadays, you can do 3D printing also, right? These 4 processes are there. If I say you have to make one piece, which one would you suggest? And why?
Probably an additive
Huh?
manufacturing process.
Which one will insist?
An additive manufacturing
Yes,
process.
very good. Because I don't need anything, right? I don't need. I have a machine. I can print it. I can make a one piece. I have to make 25 pieces. What would you suggest? Low volume manufacturing.
So a machining process.
Why machining?
So because again the equipment used is probably a little more generic and does not so
Very
it's a
good.
low volume
Very good.
manufacturing,
Very
so I
good.
don't need to invest much.
So I only lose some material because I would do certain machines. I lose some material as chips, but I'm able to make it without any special machinery with it. If I were to do casting, I have to do make a pattern, I have to make a mold. So if I have few hundred pieces, maybe I'll go for casting. If I have to make a million pieces, right? In that case, I don't want any waste. And I have large volume. So I can make a die, take a starting piece and just forge it. Right. Forging is very expensive, but if you have to make, say, hundred thousands of those or very high quantity of those, you would go with the forging process, a deformation process. So if you have to make one piece, you could go with additive. If you have to make a million piece, you go with deformation processes. If you have to make a more complex piece, which is not easy to machine, then you will do casting, because casting you can get very complex shape, although you have to do some finishing operation there. So these are the things which I want you to appreciate. What are the capabilities and limitations of the processes, right? What kind of, so if I do casting, the roughness will be very high. It will need a finishing operation. So this is the limitation. So I want you to appreciate the the capability, and B, the limitation of the unit processes, because then only you can make a wise decision there. Then I also want you to understand the physical principles underlying this process. What is the physics behind the process? How does this process work? So in case of, say, casting, you pour the material, so there's a material flow. So you need to understand that the flow should be laminar. If it is turbulent, then there would be aspiration. So you need to understand the flow, the flow of molten material. You need to understand some solidification. You need to understand that how do you design the material to go smoothly so that there is no air intake and porosity is not induced. So some of the physics behind this process you need to understand, and all this knowledge has to be applied to process selection, part design, and quality control. So these are the objectives of the course. I gave you some idea of what I expect you to get from this course. If you do this course, you should have some understanding of the unit processes, capabilities, and limitations, and you should have some understanding of the physical phenomena behind this process. Okay, and we also need you to do a lot of teamwork and group projects, because at the end of the day, when you go to an industry, you need to have a team of people to realize certain things. One guy cannot do much, unfortunately, at least in the manufacturing or product development, product building. You need a team of people with complementary skills, right? It's not like developing an app, right? It is a product. Everybody should work together and basically create a product. So it would need I'll actually, in the end, I'll show you how a product is developed. Some of the products which are developed in our labs, I'll share with you. Okay. And of course, somebody rightly pointed out the costing. Yes, money is the most important decision. I totally agree with you. So you have to make it cheap. Whatever you do, you have to do it cheap, and for cheap but with good quality. Okay. So this is these are the course. So we'll have homeworks in the courses. We'll have some exams, probably a couple of quizzes and homeworks. I expect you to not. It's very easy now to see because I have access to all the homeworks and reports and everything. So I would expect that you will respect the honor code, and the work has to be independent. I cannot emphasize enough. It has to be independent work. Independent work, because I am interested in your learning, right? I'm not interested in your grades. Let me tell you very honestly, nobody will fail this course. This doesn't apply now, although for my classes, I'm actually very particular that nobody's cell phones should be out, and you should not be peeing in the cell phone while I'm teaching. But unfortunately, I cannot enforce this one. Probably a lot of you are using your cell phones to to get this lecture. So this one is no more valid. This is for a classroom thing. Assignments will be 10% of your credit. Quizzes will be 10%. Midterm will be 25%. Project would be 20%. I would assign projects in a week or two, and I'll also assign you one of the TAs to help you. He will help you in the sense that he will try to guide you, but the guide you as in like he can if you ask him something, he will answer the question. So the onus is on you for the project. The onus is on you. You can ask questions, he will respond. If he's not responding, you can talk to me. I'll respond. But his role is to guide you. Your role is to work. He will not do things for you. You have to do yourself, but he will be able to give you suggestions, right? Suggestions to go forward. And we'll also have some sort of a weekly interaction with your TAs, so that you can update him what is going on. And we'll have multiple presentations. We'll have one presentation before midsem, and then some submissions. I would want you to basically give first an abstract of the project to basically help you understand what you want to do. And then a midterm presentation, a midterm report, a final presentation, and a final report. So there'll be 5 submissions. There'll be 5 activities in this project which will be worth 20%. And all of this is to basically make sure that you keep engaged with the project at regular intervals. I know you have a lot of courses to worry about. I don't want to overload you, but at the same time, I want you to be on top of it. End semester exam is 35%, and then total this is 100%. Any questions here on this? Okay. The question is the team project, is the project a group one? Yes, it's a group project. And by now, I think you guys have friends. So I typically don't want to assign groups. You can do a self-selected group of 4. You select yourself, and then don't complain that this guy is not working, that guy is not working. You make a team, knowingly who your partners are, and then in the end, I don't want to hear any complaints about it, because you have self-selected those 4 people, knowing very well how they are, what they are. Now you have known your friends for about a year and a half. Okay, maybe this 8-9 months will not count, but still, what would you prefer? Would you prefer self-selected, or you want me to make, because this time it's slightly different, because you may not be able to have a personal connect with a lot of folks. So if you want, I can also do a fixed assignment. Usually I don't do. Usually I have never ever assigned people, because I love people to do self-selected, because that gives them some degree of comfort and workability. So we'll have self-selected in that case. Okay. If you have any problems in getting matched up with somebody, look me up. I'll match you up with somebody.
Hello, sir.
So let me just we discussed this, so I'll just go over it. The actual word manufacturing has come from manufactus, which is manus means hand, factus means made. So manufacturing is actually handmade. Unfortunately, now the meaning is entirely different. It's actually machine made rather than handmade. But what manufacturing typically means is that you have raw materials and you do something to it, and you comes usable product. So basically, either you change the shape or properties. Now, can somebody tell me what are the properties which you can change? Shape, everybody understands, right? So you have a cylinder, you make a ball out of a cylinder, right? Or you make a free-form shape by machining. You can make a sine curve if you like, right? Very complex shapes you can create now, especially with machining. Now, my question is, what are the properties you can change?
Strength.
The strength.
Which one?
Strength.
Strength. Now, can somebody define what is strength? What do you mean by strength?
Deformation.
Pardon?
Resistance to permanent deformation.
Resistance to what?
Deformation. Permanent deformation.
Resistance to deformation. So is it modulus?
No, so the E.
When you talk about strength, right? Let's not go into technical definition. Just tell me, if you say A is stronger than B, what do you mean? What property
So
do you
me,
mean?
So A can tolerate the situation greater as
No.
compared to B.
What property? You're an engineer, Baba.
the yield strength.
Yield strength, right? So yield strength. Strength basically means yield strength, meaning you are talking about onset of plasticity. So yield strength is one thing where it starts to deform plastically. Point. So if I apply, say, some amount of force, it will result into stress, and my stresses at which, or if the diameter of the two materials are same, the stresses will also be the same for the same force. So it can take larger stresses and larger forces, right, before it deforms plastically. So that is one thing. That's one definition of strength. But that's actually not an easy way to find this one, right? If you have a nice UTM machine, you'll be able to find it. But if you don't have a UTM, it's not able. You're not easy to find it. A simpler definition would be ultimate tensile strength. You just keep on pulling it till it breaks. So strength is basically either ultimate failure or tensile strength, or yielding where the onset of plasticity comes, which basically means if I unload it, it will still keep the deformed shape, right? So that would be the strength. What is other property? Strength, and what else? Any other property? Material property, which I can change?
Hardness.
Hardness. What does hardness mean?
Resistance to local indentation.
Which one?
Resistance to local indentations.
Okay. So basically, you're reaching to indentation, basically resistance to plastic deformation. Hard basically means you do not deform plastically, right? Resistance to deformation would be hardness. Typically, hardness and strengths are generally related. Generally, okay. Any other property?
Toughness.
So
Toughness, right? What is toughness? Anybody can define toughness for me?
Withstand load without fracturing or breaking.
So toughness basically, let me just say, toughness basically means is how much energy it absorbs before it fails. So this area under the stress strain curve is toughness. Okay. If a material is brittle, right, it will just fail like this. So the area under the curve will be this only. If material is ductile, it will deform a lot. So if I have, say, a bumper in front of my car, what do I want? I want it to absorb a lot of energy and not fail immediately, so that I get less energy impact. So toughness would be something that strains a lot. And the area under stress strain curve, which basically is energy, it takes a lot more energy, would be tough to fail. So basically sigma, if you say sigma, so this is sigma d epsilon, and this sigma d epsilon under from 0 to epsilon would give you energy per unit volume. Okay, that's what is toughness. Okay, so these are the properties that you can change. So if you take a cold material, deform it, it actually becomes stronger. Hardness, you can do these matacitic processes where you can do a quenching process and make it hard. Toughness, you can change the microstructure and get tough. Smaller microstructure will be generally tough. Or you can have some sort of annealing process which will make it softer, but it will also make it more ductile. So if ductility increases, it will typically be tough, but it will be a function of ductility as well as your stress, both. Okay. Your yield stresses and ductility will basically govern the toughness. because it's the area under the stress strain curve. Okay, so we'll stop here with the material processing, and then let me just finish it up. And manufacturing can also be defined as a system or an enterprise. So basically, it's a series of integrated activities, operations involving design, material selection, planning, production, quality assurance, management, marketing. Everything comes under manufacturing. So if you want to, it's a very complex interdependent activity that's dynamic in nature. So if you want to understand right from need, because if I want to make a product, right, I need to understand if there is indeed a need for it. So I'll do a market research, I'll do a market forecast, I'll get a concept of the product, I'll make some rough sketches, make the concept of the product, get a conceptual design going. So this is what I want to make. So before iPod came into the market, right, what Steve Jobs did is there is no music system in the market. If today, if you bring iPod, it will not fly anywhere because everybody has a cell phone which has a music system built into it, right? But at that point of time, 20 years back in 2000, there was a need for that kind of a product. So you get a conceptual design, you'll make something like this, you'll come up with drawings, then we'll do product design, you'll make the specifications for the product, do some design and analysis, and then you'll make some solid model drawings, some part drawings, solid models. Then based on the solid models, you'll create a bill of materials, what materials will be needed. Then you do process planning, then you do process R&D, then you do actual manufacturing, you need toolings, jigs, machines. Then you do production control, which will be industrial engineering kind of access. Industrial engineering also totally comes under manufacturing. Routing, scheduling, production making, and then quality assurance, maintenance, inspection. Everything is part of manufacturing. Then shipping, then customer service, and finally disposal. This entire cycle actually comes under the concept of manufacturing. But we will talk about only unit processes in this course, just to let you know, because manufacturing is very big, but then the course goals are only to talk about key processes. So we'll talk about basically some of the things, like if I want to reduce weight, process things is not easy, right? If I want to make cans, if you let me just go show how cans were made from, say, 60s to 1990s, right? This is in 2009-10. This is how the can looks right here, and this is how can looked in 1955. We are able to, I think this is in 90s, but I think it's even less now. You have saved more from 18.8 grams, you went to 13.5 grams. Now I think it will be 10 to 12 grams. So over the years, you start to make thinner and thinner cans just by the process improvement, just by understanding the process better, how you can deform. And this is significant cost saving for the companies, right? So this is what I wanted to say, that this innovation, what it has done is it has enabled us to make lighter cans, which is not possible with the technology in 50s. And then if we talk about, I want something very high tolerance. What do you mean by tolerance? How many people understand what tolerance means?
So a deviation from prescribed value.
So tolerance is not deviation from described value. Tolerance basically means that you are right in some sort of allowable deviation from a desired value. That's what tolerance would be. So say if I ask somebody to make 50 mm shaft, right? You will say it's very easy to make 50 mm shaft. I can take a shaft, I can take a bar stock and turn it on a lathe, right? Very easy to do. If somebody says that you make 50 mm plus minus 1 mm shaft, very easy. If somebody tells that you make 50 mm plus minus 0.010 or 10 micron tolerance, tell me between this A and this B, what will be the cost difference? They're making the same thing. They're making the same diameter product. In one, I say that you have 1 mm tolerance, and in another one, I say that you have 10 microns tolerance. What do you think will be the difference? Anybody?
Probably close to 100 times.
No, I'm just saying that would there be a cost difference between the two? If somebody tells you make a 50 mm shaft, one guy says 50 mm plus minus 1 mm is okay for me. The other guy says, no, I want 50 mm plus minus 10 microns. Would we use the same process to make both of them?
No, sir, like precision is not accurate as in B. So we required high precision.
50 mm plus 1 mm, I can take any crappy lathe and do this. But if somebody tells me 10 micron accuracy I want, I cannot use a normal lathe machine. Either I have to use a precision lathe machine, or I have to go to a centerless grinding, which is very, very expensive. So depending upon what is the tolerance, my process changes and the cost goes significantly. The A will cost you probably, manufacturing cost will be 10 rupees. B will be 200 rupees, 20 times more. Just I'm giving you some numbers to work with. These are not literary numbers, but I'm just giving you that there will be orders of magnitude higher cost just by the tolerances. I want to understand and appreciate that. Okay. And then basically, I have talked about this mostly, that manufacturing process basically means there will be some input mass, input shape, you provide some energy and you get some output shape and output mass, right? So there can be mass conserving processes like casting, bulk deformation and powder processing, mass reducing, which is machining, mass adding, which is joining. So these two will be covered in this course. Okay. So this you all will study more and more as we go. Next class we'll do casting. So this is summary, and then what I will do is basically I'll show you a machine which we have built. This is relevant machine because this is a machine which wait. I think this is, I'm not able to play this. Yeah. So this is a machine which we have built on our lab. Okay. For some reason it was not playing there, so I'll have to play like this. So this is a additive manufacturing machine which has been designed and built in the lab. Yeah. So this is a complete automated machine with a powder delivery system which will do 3D printing on a robot. This has been totally built by the students here, and one of the students who has built is one of your TAs actually. So you'll be interacting with him. He has single-handedly designed the entire system, built it, and we're using this system for hard facing of molds, repair of those, free-form repair of the molds. You can scan the defects and basically redeposit the material locally. So this is something which we have made on the machine. The reason why it's a big deal is the strength of this material is roughly 1.6 GPa, harder than any material you know. So machining will be a nightmare of this kind of a material. Then we have made another machine, which I'll just show you here before we end the class. This is a vent cleaning machine. This we built it for Seat tires. So when they do this vent cleaning, they will use a basically a small drill to do it. So this was drill used to break, and it can go into the tire. The tire can blast. It's very dangerous. They actually lost some tens of thousands of tires order with Renault because there was one tire which has metal filling in it. So we designed a machine which could automatically identify the vents and fire a laser, nanosecond pulse laser, using a robot. So this machine we designed, built in-house. Again, Sachin was involved in this, and we went ahead and we installed this machine in Seat factory. So these are Seat officials. We trained them in our lab. And then finally, we went ahead and installed the machine. So basically, I'm giving you an idea because to end the introduction class this is the level of work which a student has done. This machine was designed by a DD student who designed the machine, who developed the entire thing, electrical systems integration, all the controls integration, Even the automation of detecting the holes, everything was done by that student. And Sachin, who would be there, who would be your TA. So this entire work has been done by students, just to give you an idea that what kind of work the students are capable of doing. Okay. So with this, I will stop here. I'm sorry I took some few minutes over. So thank you so much for your time, and we'll meet in the next class on Monday. Okay. Bye bye.